Hello everybody, we're going to begin some discussion about the idea of area and summations, which is a basic idea that will be needed to help us define a definite integral. So we need a little bit of a notation right here, but by the end of all of this, we should be able to understand the concept of an area and how we can approximate the area using plane regions and some of this area by using summations and limits of these summations. So we'll come back to that in a while. The first thing we have to start with is this idea of sigma notation. The sigma, that's a capital sigma there in Greek letter notation, is used to indicate a summation of terms. In our summation, of course, we're going from a lower bound I equals 1 to an upper bound, some number n, where a sub I, a with the subscript I, is the ith term of that summation, and I we call the index of summation. An example of how we might use this is given in the following examples right here. Let's say that we're told to take the summation from I equals 1 to 6 of the square of I. That's going to mean the following. In this case, this means that we're going to take I, starting at 1, square that value of I, and then add the next preceding value in order of our integers, starting at that point all the way to 6. So 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared plus 6 squared. Similarly, if we had another limit, lower and upper limit, we would apply those limits here. In this case, the lower limit starts at 0, so we take 0 plus 1 squared, plus 1 plus 1 squared, plus 2 plus 1 squared, on down the line. But we might recognize that these numbers gives us exactly the same value as this summation above it does. In this case, both these summations will have exactly the same value. That is, in both cases, they add up to 91. So we need to look at a few rules dealing with these areas and summations that are going to help us. The first couple of rules are going to help us deal with summations in general. One of the rules that we need to know is called the constant multiple rule. The constant multiple rule tells us that if we take a summation over some I of a constant c times a function times a sequence a sub I, then that will be the same as if we took the constant out of each summation of a sub I right here. The second rule here is our sum and difference rule. This tells us that if we have a summation in which we are adding or subtracting two different sets of terms, it will be exactly the same as if we take the summation of the first set of terms, add or subtracting the summation of the second set of terms. Note in the way that I've written this notation right here, these apply to all sequences. So if I'm using the little subscript I without an upper limit, I'm indicating that there might be an upper and lower limit right here, but any summation, however it's written, these rules would be true. There are some other formulas that can help us right here. For example, if we were to take the sum from 1 to n of any summation starting at I equals 1 of a constant, the sum will be equal to a constant times n. And we'll prove these in the classroom. If I took the sum from I equals 1 to n of I, that is 1 plus 2 plus 3 plus 4 all the way up to n, whatever that upper limit is, it would be the same as if we took n times n plus 1 divided by 2. There are similar formulas here for I squared, n times n plus 1 times 2n plus 1 over 6, and for I cubed, n squared times n plus 1 squared over 4. So how would these rules be used to help us evaluate this sum? In this case, we've got the sum from I equals 1 to 10 of I squared minus 10. Let's see how this would work. First of all, we can apply our sum and difference rule. In this case, that's the sum from I equals 1 to 10 of I squared minus the sum of I equals 1 to 10 of 1. In the first term, we're going to use our I squared summation rule. And in the second case, we're going to use our constant summation rule. So let's figure out what these are going to look like. Looking for the first term of our sequence right here, we go from I equals 1 to 10, so I equals 1 to n, of n times n plus 1 times 2 times n plus 1, all divided by 6, minus the constant 1 times our upper limit 10 right here. And now it's just up to us to work out these particular values and what they would equal. I might note that when I work these out, 6 is 2 times 3, and 3 divides evenly into 21, and 2 divides evenly into 10, so I note that we'll get 385 minus 10, which is 375, which is the summation of all of the terms if we were to take I squared minus 1 from 1 to 10. So these types of rules save us a lot of time.